This presentation is delivered by the Stanford Center for Professional Development.
Okay, well, we're down to a skeleton crew here, mostly because it's too hot outside. So we'll continue with L1 methods today. So last time we saw the basic idea. The simplest idea is this: is if you want to minimize the cardinality of x, and let's find the sparsest vector x that's in a convex set. The simplest heuristic, and actually today we'll see lots of variations on it that are more sophisticated, but the simplest one by far is simply to minimize the one norm of x subject to x and c. By the way, all the thousands of people working on L1, this is all they know. So the things we're going to talk about today, basically most people don't know. So, all right. We looked at that last time. We looked at polishing. And now I want to interpret this, I want to justify this L1 norm heuristic. So here's one. We can turn this, we can interpret this as a relaxation of, we can make this a relaxation of a Boolean convex problem. So what we do is this. I'm going to rewrite this cardinality problem this way. I'm going to introduce some Boolean variables z. And these are basically indicators that tell you whether or not each component is either 0 or non-zero. And I'll enforce it this way. I'll say that the absolute value of xi is less than rzi. Now, r is some number that bounds, for example, it could be just basically a bounding box for c. Or it could be naturally part of the constraints. It really doesn't matter. The point is that any feasible point here has an infinity norm less than r. If we do this, like this, we end up with this problem. This problem is a Boolean convex, and what that means is that it is everything is convex in the variables, that's x and z, except for one minor problem, and that is that the z's are 0, 1. Okay? So this is a Boolean convex problem. It's absolutely equivalent to this one. It's just as hard, of course. So we're going to do the standard relaxation, is if you have a 0, 0, 1 variable, we'll change it into a left bracket 0, 1 right bracket variable. And that means it's a continuous variable. This is the relaxation. And here we've simply we've actually worked out, this is simply, well, it's obvious enough, but this is simply the convex hull of the Boolean points here. Now, if you stare at this long enough, you realize something. You've seen this before. This is precisely the linear program that defines, this is exactly the linear program that defines the L1 norm. So here, for example, this says that norm x is it's an upper bound on zi is an upper bound on 1 over r xi. And so, in fact, this problem is absolutely the same as this one. And so now you see what you have. That Boolean problem is equivalent to this. By the way, this tells you something. It says that when you solve that L1 problem, not only is it a heuristic for solving the hard Boolean problem, it says it's a relaxation and you get a bound. The bound is this. You have to put a 1 over r here, where r is an upper bound on the absolute value of any entry in C. For that matter, any entry that is a potential solution or something like that. And this tells you that when you solve this L1 problem, not only do you is it a heuristic for getting a sparse x, but in fact it gives you, within a factor of r, a lower bound on the sparsity. So that's that. By the way, it's a pretty crappy lower bound in general, but nevertheless, it's a lower bound. Okay. Now, we can also interpret this in terms of convex envelope. And let me explain what that is. If you have a function, f, on a set C, and we'll assume C is convex. So on a convex set C, in fact, I should probably change this to convex set. This function is not convex. The envelope of it is the largest convex function that is an underestimator of f on C. And let me just draw a picture, and I'll show you how this works for the function we're interested in. The function we're interested in looks like this. It's 0 here, and then it's 1 over here. So that's our indicator function. And if you like, we can do this on the interval plus 1 minus 1. Okay? And so our function looks like this, basically. That's our cardinality function. And what we want to know is this. What is the the largest convex function that fits everywhere beneath this function on that interval? By the way, well, I can leave it this way. So any convex function, it's got to go through this point, it's got to go through that point, and therefore, this gives you, that's it. So no one would call this absolute value function a good approximation of this function, for sure. But it does happen to be the largest convex function that's an underestimator of it. Okay, so that's that. And then actually, you can go like this if you like, because it's on this. It's just on this one set. So that's the convex envelope. Now, we can relate it to all sorts of interesting things. I mean, one is this: that one way to talk about the envelope of a function in terms of sets is this: you form the epigraph of the function, and then simply take the convex hull. And it turns out that's the epigraph of the envelope. And you can see that over here, too. So the original function has an epigraph that looks like this. It's all this stuff, and then this little one tendril that sticks out down there. So it's everything up here, and one little line segment sticks out there. Convex hull of that fills in this part and this part. And what you end up with is the absolute value restricted to plus minus 1. So that's going to be the convex envelope here. And another interesting way to say it is this. It is, in general, it's F star star. And I don't want to get into the technical conditions, but actually the conditions aren't that big a deal. It's that it should be closed or something like that. Actually, this function here is not closed, but anyway, it looks like this. It's the conjugate of the function, which is always convex, and then that's starred. So it's the conjugate of the conjugate. Now, if the function f were closed and convex originally, this would recover f. That's kind of obvious. Okay. So for x scalar, absolute value x is the convex envelope of card x on minus 1, 1. And if you have a box of size r, an L infinity box here, then 1 over r norm x1 is the convex envelope of card x. So that gives you another interpretation. So if someone says, what are you doing? You say, oh, I'm minimizing the L1 norm in place of the cardinality. They could say, why? You'd say, well, it's a heuristic for getting something sparse. And they go, well, that's not very good. Can you actually say anything about it? And you go, actually, I can. 1 over r times my optimal value is a lower bound on the number of non-zeros that any solution can have. Okay. By the way, if you understand this, you already know something that most of the many thousands of people working on L1 don't know. You're actually now much more sophisticated. And I'll show you. And it's going to be stupid, but it's actually completely correct. Suppose for some reason I told you that x, 1, lies between 1 and 2. So it lies here. What's the convex envelope of that? Well, it's this. It looks like that. And what you see is that the function is now no longer an absolute value. It's asymmetric. Okay? So it's asymmetric. You can write out what it is. Would it be a better thing to do if you wanted to minimize the cardinality? In this case, the answer is absolutely it would be better. It would work better in practice. In theory, of course, it's better because it gives you the actual convex envelope and so on. So what that says is that when you minimize the 1 norm of x as a surrogate for minimizing cardinality, you are actually making an implicit assumption. The implicit assumption is that the bounding box of x, of your set, that the bounding box is kind of, it's like a box. It's a uniform, right? All the edges are about the same. And they're centered. If you ever have a problem where you're minimizing cardinality and x is not centered, like for example, some entries lie between other numbers, you should be using a weird skewed weighted thing like that where you have different positive and negative values. Oh, what if I told you that x2 lies between, for example, 2 and 5? What can you say then? Then x2 is not a problem because x2 will never be 0. Okay, so it's a non. Then it's easy. Okay. Well, we just talked about this. So if you knew a bounding box like this with an Li and a Ui, then, and by the way, you can find bounding box values very easily by simply maximizing and minimizing xi subject to over the set. So you can always calculate bounding box values. Now, if the upper bound is negative or the lower bound is positive, then that's stupid because it means x has a certain sign and there's no issue there. It's a non-issue. If they straddle 0, that means there's the possibility that that x is 0. And in that case, the correct thing to do is to minimize this. If these things are equal here, that reduces to L1 norm minimization. So that's what that is. This will also give you a lower bound on the cardinality. Okay. So let's look at some example. I think we looked at this last time briefly. I'll go over it a little bit better this time. We'll go over it in a little bit more detail. This is a regressor selection problem. You want to match B with some columns of A, a linear combination columns of A, except I'm telling you, you can only use as many as K columns here. So, okay. So the heuristic would be to add, for example, a 1 norm here and adjust lambda until K has fewer than K non-zeros. And then what would happen is you'd look at this value of that then. Okay, so here's the sort of a picture of a problem. It's got 20 variables. 2 to the 20 is around 1 million. And therefore, you can actually calculate the global solution. You can do it by branch and bound. We're going to cover that later in the quarter. But you can also, in this case, you just work out all millions. So, 1 million least squares problems. You check all possible patterns. And not 1 million. Yeah, this is 1 million. You just solve 1 million of them. And for each one, so the global optimum is given here, like this. And this one gives you this, the one obtained by the heuristic. And you can see a couple of things here. It looks to me like you never, I'm not quite sure here, but I think you're, for most of it, you're never really off by, well, no, here you're off by 2. That's a substantial error. You're off by 1. Sometimes you're exactly on and stuff like that. But the point is that this curve is obtained by the heuristic, which was 1/millionth the effort there. Okay. So now we'll look at sparse signal reconstruction. It's actually the same problem, different interpretation. You want to minimize norm AX minus Y. Y is a received signal. X is the signal you want to estimate. The fact that there's a 2 norm here, this might be, for example, that you're doing maximum likelihood estimation of X with a Gaussian noise on your measurement. So you have your Y equals AX plus V. Then this is prior information that the X you're looking for has no more than K non-zeros. So that's the The L1 heuristic would be to minimize this 2 norm subject to norm X in 1 less than beta. In statistics, this is called lasso here. I can't pronounce it. You have to pronounce it with Trevor Hasty's charming South African accent. I tried to learn it last time I went over this material, but I never succeeded. So I'll just call it lasso. Okay, so that's this thing. And another form is simply to add this as a penalty and then sweep gamma here. And in this case, it's called basis pursuit denoising or something like that. And I can explain why it's basis pursuit. If you're selecting columns of A, you think of that as sort of selecting a basis. So this, I guess, don't ask me why it's called basis pursuit, but that's another name for it. Okay. Let's do an example. It's actually, when you see these things, they're actually quite stunning, and they are rightly making a lot of people are interested in this topic now. Although, as I said earlier, the ideas go way, way, way back. So here it is. I have a 1,000 long signal, and I'm told that it only has 30 non-zeros, so it's a spike signal. Now, just for the record, I want to point out that 1,000 choose 30 is a really big number. Okay, so the number of possible patterns of where the spikes occur is very, very large. For all practical purposes, it's infinitely large. And here's what's going to happen. We're going to be given 200 noisy measurements, and we'll just generate A randomly. And there'll be Gaussian noise here. Okay? And then you're asked to guess X. Now, by the way, I should point something out. If someone walks up to you on the street and says, I have 1,000 numbers I want you to estimate. Here are 200 measurements. You should simply turn around and walk the other way very quickly. Okay? Get to a lighted place or something like that as soon as you can, or a place with other people. The reason is this is totally ridiculous, right? Everyone knows you need 1,000. If you're going to measure 1,000 signals, you need 1,000 measurements. Okay, so at least 1,000, right? And better off is 2,000 or 3,000 or something like that to get some redundancy in your measurements, especially if there's noise in it. But the idea that someone would give you 1/5 the number of measurements as you have data to estimate and expect you to estimate it is kind of ridiculous, okay? Now, by the way, the flip side is this. If someone told you which 30 were non-zero, you move from 5 to 1 more parameters than measurements to the other way around. If I tell you that there's 30 numbers I want you to estimate and I give you 200 measurements, now you're 8 to 1 in the right direction, or you're 7 to 1 in the right direction. In other words, you got 7 times more measurements than... Everyone following this? Okay. So, all right, so what happens is if you simply do this L1 thing, you just, well, you can see in this case, you just recover it like, I guess it's perfect. I mean, it's not completely perfect. Some of these, I think the sparsity pattern is maybe perfect. It looks to me like it's perfect. Yeah, if it's perfect, it's awfully close. By the way, what that means is that if you polish, your noise will go down lower and you'll get these very close. You won't get it exactly because you have noise. But the point is, this is really quite impressive. If, in contrast, you had used an L2 reconstruction, a Tikhonov, and you'd solve this problem, you can adjust gamma. Basically, it never looks good, the reconstruction, but this would be an example of what you might reconstruct, something like that. So this is the rough idea. Okay, so these are actually pretty cool methods. I mean, I don't really know any other sort of effective method for doing something like this. For saying, look, here's 200 measurements of 1,000 things. Oh, and here's a hint, prior information. The thing you're looking for is sparse. Please find it. And these work. I should also mention, unlike least squares is kind of nice. You know, it's a good way to blend a bunch of measurements and get a very good, it can work beautifully well if you've got like, 50 times more measurements than variables to estimate and you use least squares. Almost like magic. It's a 263 level, right? All of a sudden, from all these crazy, line integrals with noise, out comes like a head that you're imaging or something like that. I mean, it's really quite spectacular. And it kind of fails gracefully. I should add something here. These don't fail gracefully. And I bet you are not surprised that. So if you take this, which you can, all the sources on the web, everything, and you just start cranking up sigma, and you crank it up and up and up, and it'll work quite well up until some pretty big sigma. You'll give sigma one more crank up, and boom, what will be reconstructed will just be complete. It'll go from pretty good reconstructed to just nonsense very quickly. So I just thought I'd mention that. So somehow it's not surprising, right? Okay. Let me mention some of these theoretical results. Obviously, I'm going to say very, very little about it. They're extremely interesting. In fact, just the idea that you can say anything and all about it, I find fascinating. But here it is. The problem is going to be that the set C is going to be very embarrassing. It's going to be an affine set. So basically, suppose you have y equals ax, where the cardinality of x is less than k. And you want to reconstruct x here. Now, obviously, you need the minimum you could possibly have would be k measurements. So, in other words, if someone comes up to you and says, "Wow, that's good. You got my my spike signal with 30 things. What if I gave you 19 signals? That's not enough to get 30." On the other hand, if the number of measurements is bigger than the size of the number of parameters, then we're back in 263 land, and everything's easy to do. So it's trivial. So the interesting part is where m lies between k, that's the known sparsity of the signal, and the number of parameters. And the question is, when would the L1 heuristic, that's minimizing norm x1 subject to ax equals y, and notice how simple the set is C. It's the set of x such that ax equals y. When would it reconstruct it exactly? That's the question. And actually, you can actually say things which are quite impressive. And it basically says this. It says that depending on the matrix A here, But there's a lot of matrices. Actually, there's a lot of matrices that would actually work here. There's actually all sorts of stuff known about exactly what it is about the matrix A that does the trick. It has to do with coherence or something like that. And it says basically that if M is bigger than some factor times K. So this is sort of, if I gave you the hint, if I told you what the sparsity pattern is, you'd need M bigger than or equal to K. So the extent to which this number goes above 1 is how much more you need than the minimum if you had the secret information as to what the sparsity pattern was. And this is an absolute constant C times log n here. Then it says if this works, then the L1 heuristic will actually reconstruct the exact x with overwhelming probability. What that means is that as you go above this, actually the probability of error goes down exponentially. Okay? So that's it. And some valid A's would be this. If the entries in the matrix were picked randomly, that would do the trick. If A was a rows of a DFT matrix, of a discrete Fourier transform, then it would work as long as the rows are not like bunched up or something like that. Then it would work. And there are lots of others. So this is it. And these are beautiful things. It would take you about 4 seconds to find these on the web with Google to find references to and just get the papers. So, okay. So we'll go on to the second part of this lecture, and that is going to be here. There we go. Great. Okay. So we're going to look at some more advanced topics here. Just other applications and variations and things like that. So one is total variation reconstruction. I should add that this predates the current fad. The current fad, L1 fad, it depends on the field. I mean, statisticians have been doing it for a long time, like 12 years or 15 years now. People in geology, I think, have been doing it for 20. Others have been doing it probably 20 or something like that. But the recent thing actually was spurred by these results, and that's in the last 5 years, let's say. But total variation, this goes back, I believe, easily to the early 90s or something like that. So it works like this. You want to fit you have a corrupted signal, and you want to fit it with a piecewise constant signal with no more than k jumps. A simple way to do that is to trade off, x hat is going to be your estimate of the signal. You trade off your fit here. By the way, if this were Gaussian noise, that would be something like a negative log likelihood function here. You trade off your fit with the cardinality of dx, where d is a first order difference matrix. And what you'd do is you'd vary gamma. If you make gamma big enough, the solution x is constant, and then of course it's equal to the average value. As you crank gamma down from that number, what will happen is the x hat will first have one jump, so it'll be piecewise constant with one jump, then 2, then 3, and so on and so forth. Okay. So dx1, by the way, is the sum of the differences of the absolute values of a signal. This is a scalar signal for now. That's got a very old name. Goes back to the early 1800s. That's called the total variation of a signal, of a function. A signal, that's fine. And this is called total variation reconstruction. And there's a lot of things you can say about TVR reconstruction, but what happens is they actually are able to remove sort of high frequency noise without smoothing it out. And we'll see how that works. Like an L2 regularization would just give you a low pass filter and it'll smooth everything out. They're very famous here because these were some of the methods used to do things like recover these original from the wax recordings of Caruso or something. They actually reconstructed them. They got all sorts of jazz stuff from the 20s and reconstructed them using these methods, and they're amazing. I mean, sort of the clicks and pops just go away. I mean, they're just removed. Okay. So here's an example. And so here we have a signal that looks like this. It's kind of slowly moving, but it's got these jumps as well. I mean, this is just to make a visual point. There's your signal. And the corrupted one looks like this. So there's a high frequency noise added here. Okay? And if we do total variation reconstruction, these are 3 values of gamma, and they're actually chosen. one's supposed to be like too much, one's too little, and one's not enough. But you can see something very cool. The jumps are preserved. So, and that's not like that. That's not smoothed out at all. That's smoothed out perfectly. Okay? And this is sort of too much because you've actually sort of flattened out the curvature that you saw here. This is maybe you haven't removed enough of the signal, but you still get this jump here. And this might be just enough. By the way, if you were listening to this, in fact, I should probably produce some like little JPEG file. Some little audio files or something like this, so you can hear total variation denoising. It's very impressive. L2 denoising, in a minute we'll see that. That's just low-pass filtering. You have a lot of high-frequency stuff. Everything just muffled. You hit a drum, everything's muffled. The L1 stuff will actually cut out this high-frequency noise, but when someone hits a snare drum, it's right there. So it's pretty impressive. It'd be fun to do that, actually. Okay. Here's the L2 reconstruction, just to give you a rough idea of what happens. In L2 reconstruction, to really smooth out the noise, basically you lose your big edge here. And this is sort of maybe the best you can do with L2, or the best trade-off. And this would be if you still, by the way, you've still, in this case, that has not been preserved exactly. It's actually been smoothed a little bit. You just can't see it here. And you're not getting enough noise attenuation. So just to get a picture. Yeah?
In 263 we learned that even this sounds very, very good.
This one?
Yes, L2, because that's the one beat in 263, and I remember saying this also sounds very good. And why should we go the extra effort and go in for L1? I mean, knowing that
just in cases, I mean, to do things like remove clicks and pops, and if you started listening carefully, you'd find out this would not sound good at all. I mean, not at all.
Okay.
Yeah, because you'd either hear this noise, right, or you start muffling this, and that makes a drum sound like then you're not tapping a drum, you're tapping like a pillow or something like that, and it's no longer a drum. I mean, just so that's the if you listen to these things, it's quite audible. We can adjust the parameters so the 263 methods work well, which of course naturally we'd do in 263. No, wouldn't we? So okay, so okay. But actually, the total variation reconstruction is really done more often for images, and I believe it's also done even for in 3D, and I believe it's done even for 4D. So for 3D for movies and with space time. But we'll look at it in 2D, and it's quite spectacular. So here's the idea. And this is going to be very crude, and I'll make some comments about how this works. So what it is, you have X and Rn. These are the values on an n by n grid. So our grid has about 1,000 points on it. I mean, it's small, but that's it. And the idea is here's the prior knowledge, is that X has relatively few changes. So X is sort of piecewise constant. In other words, it's like a big region. It looks like a cartoon. It's got big regions where it's constant and with a boundary. So everybody see what I'm saying here? So that's so it's cartoon looking. It looks like a cartoon, or a line drawing, or whatever. All right, now this problem, you get 120 linear measurements. That's of course a big joke. You are whatever that is, 6 or 7 times. I guess you're 7 times under, or 6, whatever it is. You're some big factor under here. 8, maybe that is. I don't know. 8. So you're 8 times undersampled. In other words, I want you to estimate 960 numbers. I give you 120 measurements. These are exact. So the way we'll do this is we'll say, well, look, this says among all the x's that are consistent with our measurements. That's a huge set. In fact, what's the dimension of the set of x's that satisfy this? What do you think? What's the dimension on that? You don't have to get exactly, just roughly. What, 840 dimensions? Yeah, you get 961 points, you get 120 measurements, null spaces on the order of the difference, is the difference, right? So, I don't know, you get 8, so this is a huge number of x's are consistent with our measurements. 840 dimensional set of images are consistent. with our linear measurements. But among those, what we'll do is to pick one, we'll do this. We would like to minimize that this is the sum of the cardinalities of the differences. And let me show you what that is over here. And I'll explain in a minute how to make this better, look better anyway. It's this, that we have our grid. And basically, we're going to charge for the number of times two values are different. And that's both this way and this way. So for example, that big objective would be 0 if the entire image were constant. Otherwise, everywhere where there's sort of a boundary, you're going to get charged. Okay? So that's the picture. Now we can't solve that problem, but we can solve this variation on it. Now, by the way, when you do L1 this way on an image, and you just go, you charge for this way and this way, what happens is you're going to tend to get images, or you'll get things that they actually prefer like this direction or this direction, and you get weird things. I think we had that in maybe a homework. No, was it a final exam problem 364? Was it? I can't remember. I think it was. We made Jacob's happy face. Midterm. Final? Midterm. What? Homework. Okay, homework. Sure. Anyway, so okay. So let's see how this works. So here's the total variation reconstruction, and the summary is it's perfect.
That was 3648.
Yeah, I know.
That is homework.
Great. Okay. Good. Good. Okay. I forget too. Wait till you see the stuff in 364C.
There is 354C.
Oh yeah. Yeah. We're starting it this summer. Just for you. You're already enrolled. You'll like it. We're bringing the final exam back to that one. Except it's going to be kind of it's going to be every weekend though. 24-hour. But you're learning a lot. You're going to learn a lot though. Okay. So I mean this is, you get the idea. In this case, you recovered it exactly. So I mean these are kind of impressive when you see these things. Variations on this, by the way, are quite real. This is a fake toy example. You can go look at the source code yourself, which is probably like all of 10 lines or something. The plotting, needless to say, is many more lines than the actual code. These are actually quite real things. I mean, there's stuff going on now where you do total variation reconstruction MRI from a third of the scan lines, and you get just as good an image. So, okay, and this is what happens if you do L2. And I mean, this is what you'd imagine it to look like. That's kind of what you'd guess. And you can adjust your gamma and make the bump look higher or less or whatever, but it's never going to look that great. This is your 263 method. So that's essentially a least norm problem. There. Actually, I'm sorry, there's no gamma in this problem. That's just least norm. Okay. So that finishes up some of these. Oh, I said I promised I was going to mention how these methods are actually done. What you really want in an image is you really want your estimate is to be approximately rotation invariant. So in fact, you'll get a much better looking, visually now if you really do this, not by just taking your differences this way, but you'll also take this difference here as well, and you will, and that thing, you'll divide by square root 2 or something like that. And the most sophisticated way is to take your favorite multi-point approximation of the gradient and take the 2 norm of it and minimize the sum of the 2 norms of those gradients. That's the correct analog of total variation reconstruction in an image. And that will give you beautiful results. That will be approximately rotation invariant. Okay. So let me talk about some other methods. This is just starting to become fashionable. The L1, and there's other variations on it, and I think people call it beyond L1 or something like this, and it goes like this. So one way is to iterate, and we'll give a very simple interpretation of this in a minute. So I want to minimize the cardinality over x and c. So what you do is this: instead of minimizing the L1 norm, we'll minimize like a weighted L1 norm. Now we've already seen good reasons to do that. The weights correspond, 1 over the weights correspond to your prior about the bounding box. So that's one way to do, one way to justify weights. But the idea here is this: you solve an L1 problem, and then you update the weights. And the weight update is extremely interesting. It works like this: if you run this L1 thing, and one of these numbers comes out 0, then you get the biggest weight you can give, which is 1 over epsilon. What that means is thereafter, it's probably going to stay 0, because it went to 0 at first. Once you're 0, in the next iteration, your weight goes way up, and then there's very strong encouragement to not become non-zero. What's cool about this is if x turned out to be small but not 0, so you're actually being charged for it cardinality-wise, what this does is it puts a big weight on it. And it basically makes that one look very attractive, and it basically cleans up small ones, just gets rid of them. On the other hand, if xi came out big, you're taking that as a heuristic to mean something like, well, look, if you minimize an L1 norm and something comes out, one of the entries comes out to be really big, it basically means, look, that thing's not going to be 0 anyway. You're not going to drive it to 0. So therefore, relax and basically says reduce the weight on it. So if it wants to get bigger, let it get bigger. So this is the picture. And this will typically give you a modest improvement. Well, I mean, it'll actually give you real improvement over the basic L1 heuristic, and it typically converges in 5 or fewer steps. By the way, a more sophisticated version actually is not symmetric here with the weights. We'll see what the more sophisticated version is, but anyway. So here's the interpretation. So we'll work with the case where x is bigger than or equal to 0, and we'll do that by splitting x into positive and negative parts where those are both non-negative, and the cardinality of x is then the same as this thing. I mean, provided one of those is always 0. And we'll use the following approximation. Instead of, let me show you this. In fact, this is kind of the idea behind all of these new methods that are beyond L1. I mean, it goes back to, I mean, all these things go back to stuff that's very stupid. By the way, these things are very stupid, and yet it doesn't stop people from writing fantastically complicated papers about it, right, and making it look not stupid, but they're stupid. So let's go to 1 and stop there. Okay, so here's the function we want, something that jumps up and goes like that. Here's our first approximation. Not an impressively good approximation, not what you'd call a good approximation. And so this one says you replace it with a log 1 plus x over epsilon. And you know, if you allow me to scale it and change change various things, that's a function that looks like this. I'll shift it and scale it if you don't mind. And it's a function that looks like that. Well, let me just make it go through there. There, okay? So it looks like that. And this little curve at the bottom, that's the epsilon, like that. So it looks kind of like that, okay? I drew it with epsilon exaggerated. I really shouldn't have. Let me redraw it. It looks like this, and then got a little thing like that. That's sort of how you're supposed to see it, okay? And you're supposed to say, well, yeah, sure, okay. This function here is a way better approximation of this thing than this, okay? What? You don't think it is? It's not convex. You're very well trained. Right. So, I can tell you a story. A student of Abbas's went into, where they were just talking to Abbas, and Abbas said, yeah, but then you could do this problem, and maximize the energy lifetime of this thing and blah, 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 like that. And the student stepped back and he said, are you crazy? And Abbas said, no, what's wrong with that? And the student looked at him and said, that's not convex. And then he came to complain to me. He said, what are you doing? So, yeah, all right, you're right, that's not convex. Okay. But it's okay. Now you're okay. You can handle it. So in fact, this method is, in fact, not only is it not convex, it's concave. Now, if you have to minimize the concave function over a convex set, when we did sequential convex programming, you saw that there's a very good way to do that. And it's really dumb. I mean, what you do is you take a certain x, you linearize this thing at that point, and you optimize. No trust region, nothing, and you just keep going. If you linearize this, basically you get this thing here. This is a constant and it's totally irrelevant when you linearize, and you actually get this. And in fact, part of that is a constant too, like this part, okay? And in fact, it's the same as minimizing xi over this. And guess what? Sequential convex programming applied to this non-convex problem, which is supposed to fit the cardinality function better, yields that exactly. Okay? So this is really an iterative heuristic. It's the convex-concave procedure for minimizing a non-convex function, which is a smooth function, which is supposed to approximate the, what do you call it? It's supposed to approximate this card function. Okay? By the way, there's lots of other methods, and I can say what they are. Here's a very popular one. All of these work. That's my summary of them. Lots of papers coming out on all of them. Here's another one. I don't know. Here's one. You don't like, let's just do on the positive. You don't like x. How about x to the p for p less than 1? So these functions start looking like that. And the small, if you make p really small, they look just like that card function. And by the way, this leads some people to refer to the cardinality as the L0 norm. Now let's just back up a little bit there. And too many people have already said that, so you can say it. I cannot bring myself to say that. Because, you know, there's no such thing as an LP norm with p less than 1. Because it's not convex. The unit balls look like this. And then I can't even say it, you see? That's what happens if you learn math when you're young. That is not the unit ball of anything. And you should not say that. You shouldn't say that. And yet you'll hear people talk about LP norm with p less than 1. And it's not convex, it's not a norm, blah, blah, blah. So the methods work like this. In fact, you tell me, let's invent a method right now. How would you minimize this? Approximately and heuristically and so on. By the way, if you minimize that, you would get a very nice sparse solution. Very nice. How would you do it? You just linearize this thing. And what would you, and what in fact would you be doing at each step? And if you did the convex concave procedure on this guy, you'd be solving an iteratively reweighted L1 problem. Okay? And the only thing that would change is your weight update would be slightly different from this one. But your weight update would be reasonable and always do the same thing. What happens in a weight update is this. Entries that are big, you just say, screw it, that's probably not going to be 0, and you reduce the weight. Entries that are small, you crank the weight up. If that thing is already 0, that's a strong inducement to pin it at 0. If it's small, though, that makes that thing a very attractive target for being zeroed out. And that's what drives the cardinality down. Everybody got this? So that's the idea. Okay. Here's a very typical example. Is you want to minimize the cardinality of x over some polyhedron. And the cardinality drops from 50 to 44. Not that impressive. And if you run this heuristic, I guess 6 steps, it converges actually after a couple. It will convert, it'll stop out at, no, sorry, let's see. Here we go. L1 gives you 44. And the iteratively we rated L1 heuristic gets you 36. The global solution probably found for this problem in a long time, later in the class, is 32. So just to emphasize again, we're not actually solving these problems. These are heuristics. But they're fast and they're good and so on and so forth. By the way, the fact that you're not solving the problem, if the problem is for example, arises in a statistical context, I think means it doesn't matter at all. Right? So, because you don't get a prize for getting the exact maximum likelihood estimate. Maximum likelihood estimate is itself, in some way, it's just a procedure for making a really good guess as to what the parameter is. And it's backed up by 100 years of statistics. Okay. If you miss that, and by the way, even if you do perfect maximum likelihood, as any statistician or anybody who knows anything about it will tell you, you're not going to be getting the exact answer anyway. That's just something which asymptotically will do as well as any method could, or something like that. That's its own thing. Now, by the way, for engineering design, that's a different story, right? You find a placement of some modules on a chip that takes, 1.3 millimeters square as opposed to like 1.6. That's real. That's real. That's unlike the statistical interpretation. But still. Okay. So let's look at an example of that. It's a fun example. It's just detecting changes in a time series model. So let's see how that works. We have a two-term ARMA model. Or I guess people call this no, sorry, it's not ARMA. It's AR. I think actually people call this AR2. Okay, so it looks like this. Y of t plus 2 is equal to a coefficient times y of t plus 1 plus another coefficient times y of t plus a noise, which is Gaussian. Now the assumption is this. These coefficients here are mostly constant. And then every now and then when there's a change in the dynamics of the system. And one or both of those numbers changes. Okay? You'll be observing merely y. And your job is to actually estimate A and B. And in particular to find where the changes are. So let's see how that works. By the way, well, it doesn't matter. I mean, I was going to make up an application of it. It basically says, the changes could tell you something about a failure in a system or something like that, or a shock in a financial system or economic system, something like that. Okay. So here's what we'll do: is you're given y. This is a negative log likelihood term here with some constants. That's a negative log likely. This is an implausibility term because, for example, if you run up a giant bill here, it's asking you to believe that the V did some very, very unlikely things. That's what this term is. And then here we add in actually it's a total variation cost. It basically says it penalizes jumps in A and B in the coefficients. Now, by the way, if I make gamma big enough, A and B will be constant. Okay? If I make them 0, then I will make this thing 0 because I can adjust my A and B, in fact, many ways to get absolutely perfect fit here. Okay? So here's an example. Here are how A and B change. So A is this, and then I guess, I don't know, I can't see that, but let's say at t equals 100, it changes to a new value. B is here, and a 200 pops up here. So there's 3 changes. And you can sort of visually, if you squint your eyes, you can see the change in the dynamics of the system here. That if you look left of there, you get one kind of dynamics. You can see a little, with a little squinting, you can see that the dynamics on the left in between 100 and 200 looks different. And again, between 200 and 300, well, it helps that I've told you what happened. But it's certainly consistent. Now, the interesting thing, though, is imagine I hadn't told you this. I don't know that it's that obvious. I mean, certainly this doesn't look very much like that. But would you really know that something happened here? I don't know. You could. I could have made the coefficients change in such a way that your eyeball, you couldn't do it. So if you run this total variation heuristic, on the left, this is the estimate of the parameters. And I want to point out this thing is already very good. It's estimated the parameters to be here. It jumps down and it does some weird thing here. I can explain that a little bit here. It's some little false positives. That's a false positive where this thing jumps up. Every time this thing jumps up, there's a bunch of false positives in here and some false positive jumps in here and so on. But actually, you know what? This is not bad at all. Not bad at all. This is kind of, it's kind of saying that there are weird changes in here and here. If you do the iterated heuristic, you can actually see visually exactly what happens. By the way, this guy is pulled down here because it's charged a lot. It only makes this big shift for which it pays a lot in this objective to try to make this overall objective small. But what happens is actually really, really cool. What happens is this. If you iterate it, this difference is really big. And on the next step, it's going to get a less weight. So it basically says, oh, you really want to jump here? No, I'm going to charge you less for the jump at this time step. Here, these little guys, by the way, where it's flat, it says, okay, you don't want to jump at all. I'm going to charge you the maximum amount. That's the 1 over epsilon in the weight. And these little ones, that's what these iterated L1 heuristics do. They go up and they clean up things. They just get totally nailed, and that's the final estimate there. And you can see that it's much, much better. I mean, you're actually tracking the parameters very nicely. You might ask, why the error here? Why the error here? Why did it miss the time point here? And the answer would be because there was noise. That's why. But it's awfully good to do this. Okay, it works very, very well. Okay, and our last topic is going to be the extension of these ideas to matrices and rank. So, if you have cardinality of a vector, that's the number of non-zeros, there's a very natural analog for matrices, and that's the rank. And by the way, both of these things come up as measures of complexity of something. So, in other words, sort of the complexity of a set of coefficients is something like, I mean, this is very rough, number of non-zeros or something. And the complexity of a matrix also comes up a lot, and that's the rank. Now, a convex rank problem, that's a convex problem, except you have a rank constraint or a rank objective. These come up all the time. And they're actually related. If you have a diagonal matrix and the rank of it is the cardinality of the diagonal, that's kind of obvious. But the interesting part is, what's the analog of the L1 heuristic? And it turns out it's the nuclear norm, which is the dual of the spectral norm, or maximum singular value. And it's the sum of the singular values of a matrix. So that's it. It's not simple, but that's what it is. It's the sum of the singular values. And that's the dual of the spectral norm, which you probably didn't know, but it kind of makes sense, because somewhere in your mind you should have this map there that associates, well, it should associate LP and LQ, where 1 over P plus 1 over Q is 1. But particular pairings should be burned into neurons directly. That's 2 and 2. So dual of L2 is L2 type thing. And dual of L1 is L infinity. Dual of L infinity is L1. These you should just know. So it shouldn't be surprising that if it's the maximum singular value, that's like an L infinity on the singular values, roughly, that the dual norm should be the sum of the singular values. That's it. Now, if a matrix is positive semi-definite, then symmetric, positive semi-definite, then the eigenvalues are the singular values, and the sum of the singular values are therefore the sum of the eigenvalues. That's the trace. Okay? Whereas for a vector, if I have a non-negative vector and I take the one norm, it's the same as the sum. So, oh, and by the way, that's why a lot of things I would still call them sort of L1 heuristics, but you might sort of grep through the paper and not ever see never see L1 mentioned. Because if a vector is non-negative, it's just the sum. But L1 sounds fancier, so than to say L1, than the sum. The sum heuristic seems kind of dumb. Okay, so this is the nuclear norm. And we'll do an example. Actually, it's a very interesting example. It goes like this. You're given a positive semi-definite matrix, and what you would like to do is you want to put this in a factor model. Now, a factor model looks like this. It's an outer product, a low-rank outer product, a low-rank part, plus a diagonal. And it would come up this way. It basically says that if that's the covariance of a matrix, it basically said that random variable is explained by a small number of factors. In fact, it's the R is the dimension of F, the number of columns. It's a small number of factors, and then D is sort of an extra variation. So this would be the factor model. Now, by the way, there are some very easy ways to check factor models. If D is 0, how would you approximate? How do you approximate a positive semi-definite matrix as just low rank? How do you do that? I give you a covariance matrix, like the covariance matrix of 500 returns, and I want you to tell me, approximate it as a matrix of rank 5. How do you do it?
SPD. You just take the
SPD.
SPD first.
Right, symmetric. So you should say eigenvalue decomposition, but it's the same as the SVD. So you take the eigenvalue decomposition, you take the top 5 ones. So we know how to do factor modeling without this thing. But if I want to, let's do one more. How about factor modeling plus, like, suppose instead of D, this was sigma squared I. Can you do factor modeling for that? How?
You detect the first one, the rest of the eigenvalues are almost identical, and then you can subtract.
Exactly. So the way you know it is you'd look at the eigenvalues of something, and you'd see 5 large ones and a whole bunch of small ones all clustered, and that would be your hint. Okay, so that would do that. That would be one way to do it. So you can do this but when these actually numbers are all different, no one can solve that problem. Actually, it's a hard problem in general. Well, in any case, this is the simplest factor modeling problem. So C is a set of acceptable approximations to sigma, and they could be. I mean, it could be simple, like some norm ball, or it could be very complicated and statistically motivated. For example, it could be a Kullback-Leibler divergence, which would be this for a Gaussian random variable. Okay? And that's just a very sophisticated way of saying that the two matrices are close. The two variances two covariances are close. This is the one that would give you the statistical stamp of approval. The statistics stamp of approval would come from using something like that. Now the trace heuristic for minimizing rank is pretty simple. It goes like this. X plus D is your original matrix, and so your variables here are going to be capital X, and this should either be, well, I should either write, capital D is the diag of little d, so but anyway, it doesn't say that here, which is weird, but that's it. So this would be the problem, and that's a convex problem. If you put rank here, it's a convex rank problem. So we'll look at an example. So here's an example where, in fact, I have a bunch of data which are, well, we know it. It's actually generated by 3 factors. Right? So what happens is you get snapshots of 20 numbers. They're all varying. They're random. You look at these 20. You look at a bunch of these things. You get a full covariance matrix, full rank, but it turns out that three factors describe it, plus the diagonal elements. By the way, if these were asset returns, the diagonal elements would be called the firm specific. That's the firm specific variation. And basically, it said that you have a bunch of factors. I think one is the overall market typically. Then you get some other things, some very obvious things. If you look at factor models in sort of finance, you'd get these things. And then the D's are the firm specific volatilities. Okay, we'll just use a simple norm, a norm approximation, and you get a trace. You get a trace heuristic that looks like that's the convex problem. And what we'll do is we'll generate 3,000 samples from here. Now, by the way, you were estimating, I guess it's 20 by 20 covariance matrix. You got about 200 numbers. So you're maybe about 15 times as many numbers or samples as there are numbers you're supposed to get. I guess each sample is 20. So, okay, it's a couple of hundred times in terms of the estimate. But you're estimating covariance, so, okay. And this is sort of what happens. It's rank 3. And what happens is as you crank up beta, you start with a rank. By the way, the top rank is 20. But you immediately get a 15 rank model. Then as you increase beta, that multiplies the trace thing or something like that. What happens is the rank of that X goes down and down and down. You get a very steep drop down at 3. And by the way, this is the hint that rank 3 is going to give you a very nice fit. You keep going. If you increase beta enough, it goes down there to 2 and then stays there. Actually, I guess this would go down to 0 at some point. We didn't show beta that large. What's interesting is as we scan beta, this shows the eigenvalues. And so up here you have 15 non-zero, and you can see at different values of beta, eigenvalues basically being extinguished. They go to 0. And so what happens is right here, you end up with 3 from here on. And in fact, these are the right ones. So if we take beta as some number in here like this, we actually do get a rank 3 model. You can do polishing in a case like this too, obviously. Well, you can figure out what polishing is in this case. But in this case, if we take 0.1357, that's the knee of the trade-off curve, you find that the angle between the subspace, which is the range of x, and the range of FF transpose is 6.8 degrees. And that we nailed the diagonal entries. We actually got the firm-specific volatilities within about 7%. So this is just an example of this kind of thing. Okay, so this actually pretty much covers up the whole topic of sort of L1 and cardinality. And the idea is, instead of just thinking it as sort of a basic method where you just reflexively throw in an L1 norm, actually these extensions show that, first of all, it comes up in other areas like rank, minimization. These iterative methods, actually very few people know about them. They're not even used. Most people aren't even using polishing. Most people aren't even using the asymmetric L1 stuff. So if you're interested in getting sparse solutions, there's actually better things than L1 available. And certainly these things like these LP, I can't say it, LP norms, LP measures. I don't know. I don't know what word to say there that is okay. I'll just say it, LP quote norms unquote for p less than 1. Those work, these log approximations and these iterations. All these things work. And I should also say, so I guess Emmanuel Candace and I had a long conversation like a year ago, and he said that L1 is the least squares of the 21st century. So, and yeah, okay, that's a good. I mean, that's good actually. It's not bad. I think it's a little bit of an exaggeration, but it's not too far off, right? It basically says that they're going to be the same way everybody needed to know about least squares, and throughout the 20th century, eventually everybody did. And by the way, least squares, I mean fancy methods like Kalman filtering and quadratic control and things like that. If you call that least squares, then a lot of signal processing and image processing and all sorts of other stuff ended up being least squares, period. And I think a lot is going to end up being L1 as people move forward. So, okay, so we'll quit here unless there's some questions about this material, and then the next topic is actually going to be we're going to jump to model predictive control. So that's going to be our next topic. Good. We'll quit here.